Welcome to another Cohere for AI talk. This one is Cohere for AI presents Learning by Distilling Context with Charlie Snell. Charlie Snell is a PhD student at UC Berkeley. He's in many different interesting groups. He's part of the Berkeley Artificial Intelligence Research Lab, the Robotic AI and Learning Lab, and the Berkeley NLP Group. And without much ado, Charlie, please take it away.
Thanks. Yeah, so I'll pull up my slides. All right, I'll get started. So yeah, this is my talk on my recent work, Learning by Distilling Context, with my co-authors, Dan Klein and Richie Zhang. So to get started, I think it's obvious to say that language models have shown to do some pretty surprising and impressive things, like solving pretty non-trivial math problems, writing lots of pretty complicated code, and also like doing these sort of creative writing things, to the point where it's quite surprising. And while a lot of this is lots of data and lots of compute that's powering this, there's sort of two other big components that are behind some of these abilities. So one is really long prompts. So, on the right is the prompt for Google's like Minerva model. And you have this long prompt with a bunch of different math questions. And then the left is like this long prompt from Anthropic's chatbot. And they have this huge prompt that goes through a whole bunch of different chat scenarios. These prompts sort of, provide the model with context for like how it's supposed to behave. In addition to these long prompts, there's also really long reasoning chains. And so if you want to ask the problem, like the model, like a difficult math problem, it's going to have to go through these like long reasoning chain to, get an accurate answer. If it doesn't do this, it will more likely get the answer wrong. And so these are both really cool and also really important for the model's performance. However, there's some things that are a little bit weird about this. And this might sound obvious, but the language models don't internalize the performance gains given by these prompts. So the prompts in the scratch pad. So like, it doesn't remember anything. For example, like once the prompt's gone, the performance is gone. So like you might give the model a prompt and a scratch pad or a reasoning chain, and it, it can get 90% performance on the task. But once the prompt is gone, it doesn't know what to do and performance goes down to 10%. This seems kind of obvious, but if we think about this as a limitation, we might be able to come up with some like better solution or some new paradigm for looking at these kind of problems. So there's a couple of reasons why this might be undesirable. One is the context tokens themselves involve inference compute. So if you have a long prompt, you're using more compute the longer that prompt becomes. Additionally, if you're generating a long reasoning chain, every additional step in the reasoning chain is sampling more tokens and thus using more compute, taking more time to get to the answer. So that's one sort of cost here. Another is that the language models fundamentally have these finite context windows. So the set of problems we can sort of ask our language model is limited by, the set of prompts we can fit inside of their context window. And, or the length of the reasoning chain that, the language model needs to solve the problem. So these two are sort of limitations. And if we assume that in the future, people are going to be using language models or related technology to complete increasingly complicated tasks that are going to require more background knowledge and longer reasoning chains. If we assume this will be true, then these two things are kind of limiting. So we can look to overcome this, we can look at like how humans do it for maybe some loose inspiration. So the first thing to note is that humans are pretty slow at performing cognitive tasks. We have limited working memory, and so we have to like, typically work on a piece of paper and work through our work through difficult problems, we need to think, sort of step by step. One way to get around this is by practicing. So the more we practice a particular skill, the more the knowledge gets distilled deeply into our memory, and we can sort of do it more quickly and, with fewer step-by-step processes. By, distilling or like practicing more and more simple tasks, we can, build up to doing more and more complicated tasks and build up our knowledge and skills in this way. So, and a very straightforward example of this could be, for example, suppose you want to, dial your friend's phone number. The first couple times you might need to actually like, consciously recall your friend's phone number or even like go look it up somewhere. After you've done this a whole bunch of times, the act of dialing your friend's phone number will become kind of distilled into your muscle memories to the point where like you won't even have to think about it. It's just, something you do. And this is sort of what we as humans do, is like if we practice something enough, it becomes sort of deeply distilled into us. And so in our work, we sort of look at this idea of context distillation as potentially a way to implement these kind of processes in language models, this kind of process of practicing and distilling information deeply into the model. So to just give a high level, look at what we're doing here, basically the idea is to train the language models to internalize context tokens. So context tokens could mean either a prompt or, like a reasoning chain, or we also call it a scratch pad. So we have sort of two models here in our distillation process. One is the teacher and the other is the student. So the teacher has access to a prompt and it has the ability to generate a scratch pad before its final answer. The student doesn't have access to either of these. So it has like a more minimal prompt that doesn't really describe the problem, or fewer tokens. And it's supposed to just directly generate the answer without the long scratch pad. And the idea is we're going to use this teacher that has these extra context tokens in the form of a prompt and scratch pad to train the student. And so through this distillation process, you can sort of imagine that it's sort of internalizing these context tokens into the model. So to give like sort of a more detailed overview, there's sort of a few steps in this process. The first is we're going to sample some input from the input generator. So it could be like, in this example, it was like an addition problem. And that gets inserted into the teacher and student prompts. So you sample an input question, insert it into the prompts. And then you're going to, from the teacher, sample a scratch pad and final answer. And then you're going to extract the final answer from the teacher's output, so bypassing the scratch pad. And then you're going to train a student to directly predict the final answer without the scratch pad, conditioned on this sort of more minimal prompt. So that's sort of the overview. And I'll go a little more into detail into each of these steps. So firstly, you may have, this word context distillation has distillation in it. And, there's a traditional notion of what distillation means in machine learning, and context distillation does, build on a lot of those ideas, but it's also fairly different in a number of ways. The main way is that, traditional distillation in machine learning, you have the teacher's parameters being different from the student's parameters at initialization. And it's this difference in parameters that drives the distillation process. So the student learns from what's in the teacher's parameters, sort of. In contrast, context distillation, the student and the teacher initially have the same parameters. The distillation process in this case is instead driven by the difference in the context tokens that are available to the two models. So the teacher has prompts and scratch pads, the student doesn't. Now to define the individual components of our framework for context distillation more clearly. So first we have this input generator, which represents like the core inputs to the task. Was there a question? what is meant by Scratchpad. So Scratchpad that's a good question. Scratchpad is referring to what I was also calling, there's a bit of two terms I was using here. Previously, I was calling it a reasoning chain, but a Scratchpad is just this process where you give it this question, add 11 and 41, and then it goes through sort of this process of like step-by-step reasoning before it outputs the final answer. So this sequence of text here that it generates would be the Scratchpad. Yeah. So the input generator considers these like raw inputs, which could be like the addition problems that we saw previously. And yeah, it's like the first step in the process. So it could be an addition problem, or it could be something like a movie review. Suppose you want to like, your task is to classify the sentiment of movie reviews, then the inputs would be the movie reviews themselves. And the input generator can produce these inputs by either like some rule-based method that, you know, maybe just generates random strings or synthesizes the strings. Or it could be, you know, just a pool of like unlabeled input data, like training data that you just sample from, or you could generate these input strings by just prompting another language model, generate movie reviews, and get a bunch of different movie reviews sampled from the language model. So that's the input generator. And then the prompt templates. So the teacher and student have this function, which is the prompt template. And these basically just transform task inputs. So like the addition problem or the movie review into a full prompt. It basically just inserts the task input into a larger prompt. So they're here, and like this would be an example, like you take a movie review, like I have a mixed feeling, and insert it into this larger prompt. The next component is the answer extractor, which pulls out the final answer from the teacher's generation. So it generates a Scratchpad or reasoning chain followed by the final answer. And then the answer extractor is a function which takes this text in and pulls out the final answer from that text. This is used for training the student. So here's an example. I have this reasoning chain followed by like the answer 52, and then you extract 52. Okay, so those are all the key components of this context distillation framework that we're using in our paper. And now, given all these components, we can define like what the actual distillation process looks like. So on a high level, the idea is we're going to train the student to maximize the likelihood of the final answer extracted from the teacher when given the student's prompt template. So you can look at this equation to sort of make sense of this sentence. First, you sample a raw task input, and then you insert that input into the teacher's prompt template and sample an output. And then you extract the final answer from the like Scratchpad plus final answer output, and you train the student who's given, you know, a more minimal prompt than the teacher to maximize the likelihood of that final answer. So you're training it to just predict the final answer. So hopefully you can make sense of that from this diagram as well. That's basically the distillation process. Now, once we have this distillation process, we can do some interesting things. So I guess normally when you prompt a model, you can only like give it a single prompt, and it's kind of awkward or unclear how to, you know, take multiple prompts and, you know, get a model that can handle all of them at the same time. Context distillation sort of enables like a natural way of doing this. So there's sort of two ways you can combine multiple distillation steps or distill multiple prompts. One is by simultaneously distilling, you know, different prompts at the same time. So you could have one prompt that, you know, tells the model to classify movie reviews, and another which tells it to do addition problems, and maybe the student is given a slightly different minimal prompt to distinguish these two, like movie review versus addition problem. And you can distill these at the same time. You can also do, so we call this simultaneous distillation. You can also do recursive distillation, which is like, maybe you want to override or update knowledge distilled from a previous prompt. For example, maybe you have a prompt which states like a fact. It states Joe Biden is president. And the model is supposed to be able to use that fact whenever it's necessary. Once Joe Biden, once you get a new president, you're going to have to update that fact. So you're going to have a new prompt with the new fact and override the previous knowledge. So recursive distillation is this process of like overriding or distilling a new prompt that overrides previous information. So you can do this by just sort of chaining distillation. So once you've distilled it into a student model, you take that student model and use it as the new teacher, given a new prompt, and distill it into a new student that has the updated knowledge.
Hey, Charlie, can you go back to the sampling part real quick? Yeah, so you sample different completions, is that it?
Yeah.
And then you fine-tune the model to predict the different samples.
Yeah, to predict the final answer.
Okay, and you said you approximate the distillation loss.
Yes. Yeah.
Okay.
Do you have a question about that? Because I do have this on the next slide.
Oh, it's on the next slide. Okay.
Yeah. Yeah. So it is correct that like we have this loss, but we need a way to actually approximate it. So typically how we do this, firstly, we should note that the process by which we do the distillation is we first generate a bunch of samples from the teacher and then train the student. So we're going to like sample an input, sample a completion, and then sample a bunch of input and completion pairs from the teacher. And then build this big data set of input completions and then go fine tune the student with this data set. That's sort of the process by which we actually implement this. And the reason is because we can't fit two big models in memory at once. We can't, fit the teacher and the student in memory at the same time. It's just an implementation detail. But this gives rise to like how we actually approach approximating the distillation loss, this implementation detail. So there's sort of a couple ways you could approximate it. One is you could just do maximum likelihood on the final answer tokens. So you sample this, you get the tokens, and you just maximize the likelihood of those tokens from a bunch of samples. This will give you sort of a higher variance estimator, but you don't have to store much in your data set. You're just storing like a few bits for each token. Another way, which looks more familiar to like traditional model distillation, is to use the like full logit information output by the teacher at each token to minimize like a token level KL divergence. So, in the final answer for each token, you output like all the probabilities from the teacher, and then you train the student to like mimic this. This will give you a much lower variance estimator of this loss function, but it will use a lot more memory because we're going to have to store all these logits for training our student, which could actually be kind of impractical. This gives rise to sort of a third approach, which gets at sort of like a middle ground between these two, which is to form an empirical distribution of the teacher's output probabilities. So at each token, the teacher outputs some probabilities. We can estimate this probability distribution by sampling, say, 100 indexes from the full logits and store just these 100 indexes such that they represent like an empirical distribution of the teacher's actual logits.
So you sample the indexes from the logit distribution.
Yeah.
You sample them according to their probability, or?
Yeah.
Okay.
So it's like an unbiased approximation. Yes, so basically when we do this, we only have to store the like 100 indexes that we sample from the teacher rather than the 60,000 logits. So this uses less memory in our data set. And it sort of strikes a middle ground between the variance of 1 and 2.
Cool.
All right, so that's sort of the summary of like the core method or the core framework that we're discussing here. And prior works have explored, different aspects of this idea of context distillation. So parts of the method itself aren't necessarily novel, but the main novelty of our work is we sort of look at context distillation as a general method for training language models. And like in the sense that like in some cases it might be preferable to like fine tuning depending on your use case. So we show this in our experiments by demonstrating that there's context distillation can learn from abstract instructions and natural language explanations, concrete training examples just like normal fine tuning can, and it can also learn from step-by-step reasoning processes. So the second one, normal fine tuning can cover, but the first two are always sort of unclear how to learn from. So we propose that context distillation is sort of like a general method that can effectively learn from each of these kinds of information. And so I'll go through the experiments. We have like 7 different hypotheses in our experiments that we verify, and I'll sort of walk through them. Each hypothesis covers like one of these different use cases. So first, we'll look at learning from abstract instructions and explanations. The setup of these experiments are, we have this 11 billion parameter T5 teacher model, which is fine-tuned. So the T5 model on its own isn't super. Oh, there's a question. Will it be different zero shot for different tasks as well, or only for which it is distilled? I guess by default only for which it is distilled, but you can also like mix in other task data if you want it to be able to do other tasks. So in the last experiment, we sort of do this where you can transfer some of the abilities of the distilled model to other tasks. But by default, yeah, it's just zero shot for the task which it's distilled. Yeah. So so in this case, the setup is we have this instruction tuned 11 billion parameter model. We instruction tuned it on this data set called natural instructions V2, which is just a data set that includes like these task descriptions followed by some positive, negative examples and natural language explanations of each of the examples to put in a prompt. And then you can like sort of train a model that's responsive to prompts, because the T5 model out of the box is not super good at responding to like instructions. So we obtain this model, and then we distill 10 different tasks from the natural language V2 test set to verify our experiments. And so the setup sort of looks like this, where you have like a description of the task. You're going to classify reviews. Here's an example input. I'm impressed by the plot, everything in between. Here's an example output. And then you might have a natural language explanation of the like why this is the right answer. So answer is supposed to be 0 when it's ambiguous. And then, that's a prompt describing the task. And then, you give it an input and ask for an output. So that's sort of what the natural instructions data set looks like. And our goal is going to be to distill these, what we would call abstract instructions, which is like this instruction of the prompt, into a student model. So to do this, we're first going to state the hypothesis that context distillation can internalize these instructions. And to test this, we're going to create a teacher prompt that has the instruction, 2 positive and negative examples, followed by the actual input, and the student, which has none of this information, just the input. So we're supposed to distill like all the tokens in this, abstract instruction prompt, which looks something like this, into the student. And we see like, okay, so the teacher itself has a 43.4 Rouge L performance across the 10 tasks we distilled on average. And then before distillation, the student, you just give it the question, it doesn't know what to do, right? There's no instruction, so it has a really low score. But after you distill it, it gathers a lot of the information that the prompt was providing to the teacher. So we're sort of able to actually distill, internalize these abstract instructions in a sense. And so, yeah, the takeaway here is that we can actually internalize some of the knowledge present in these task instructions. The second hypothesis to take this further is to specifically ablate, like, how much can we learn from the natural language explanations? So in general, I think it's unclear how to learn from things like natural language explanations. So like if you have an explanation that says like, has this information like answer 0 when it is ambiguous, how do you actually learn from that information? And this is one thing that sort of context distillation brings to the table, is you kind of can learn from this information if the teacher is able to, respond to this natural language explanation. So to ablate this effect, we basically have a teacher prompt which contains, the task instruction, 2 positive and 2 negative examples, with all examples having an explanation of the answer. And then the student prompt has just the positive and negative examples, no explanation. And we see that like, so we're basically testing how can we internalize just the tokens from the explanation, and do they help the student? And so to evaluate this, we measure how much do the explanations help the teacher, which is the in-context margin, and how much does the student improve after distillation, which is the distillation margin. So we see if the explanations help the teacher more, the student will learn more from them during distillation, is essentially what this is showing. So each of these points is a task. So the student's effectively able to learn from the teacher if the teacher is sort of responsive to the natural language explanation. So then lastly, this is probably the most complicated experiment, but so just sort of bear with me here. The hypothesis here is we can use the recursive distillation thing I described. We can use recursive distillation to override past updates or override previous abstract instructions. So we sort of test this by training the student to associate a task ID with the instruction. So, and then we override these task IDs. So the teacher is given a task instruction and then 2 positive and negative in-context examples, followed by the input question. And then the student is just given this task ID. So maybe one of the tasks is classifying movie reviews. We might associate that with task ID 0. And then another task is add these numbers, and that's task ID 1. So when we ask the student, perform task 0 or perform task 1 on this input, then it should be able to, perform the correct task. And so the basic setup here is we're first going to distill 4 different tasks with 4 different IDs associated with them into the student. And then we're going to reshuffle these task ID associations and then recursively distill the new associations and override the previous ones. And then we're going to return to step 2 and reshuffle and do this again, and we can keep doing it. So we're seeing how much can we update the knowledge that was distilled into the student. And so I guess there's a big consideration here is like, if you do this recursive distillation, the student might actually forget to respond to these task instructions. But we actually find that this isn't an issue. So we look at the results, isn't too much of an issue. So we look at the results. We have the teacher's performance, the student before distillation, and then the student after distillation. It actually is able to, respond to the correct task ID and, make the correct predictions for each of the tasks is essentially what this is measuring, the Rouge L score on each task. And then here we're showing that, after each round of recursive distillation, the student's performance does, so we did 3 rounds. The student's performance doesn't, come down because it maybe forgot how to respond to instructions or something. It still works. So it's showing that you can kind of combine multiple distillation steps to recursively override past updates. So that's sort of our experiments on the learning from abstract instructions. Now, learning from concrete examples. The basic idea here is that you could prompt the model with, say, 4 or 8 training examples to help it learn to complete a task. And then you could distill these 4 examples and then maybe prompt it with 4 more to help it learn to complete the task. And so in this way, you can kind of think of context distillation as a way of learning from a small data set. Instead of doing traditional fine-tuning or gradient descent on the data, you could just distill multiple prompts with different training examples. And so to test this, we're going to look at the Spider text-to-SQL dataset, which is a semantic parsing task, which basically involves, given a database schema and a question, predict the SQL query that would answer that question if executed under the database. So an example is down here. Maybe you have like some database schema, like create table, and then you might ask a question like, how old is Peak? And then it's supposed to generate a SQL query that would be able to fetch the answer to this. And so, yeah, this is a task which prior work has demonstrated that language models are pretty good at, they're actually able to learn something from the in-context examples on this task. So this was a good setting to test this in. And we measured the exact match accuracy, which basically determines, like, does the model generate the ground truth SQL query, which is one standard way to measure performance. There's others, but it's a straightforward evaluation metric. And then for the base language models on these experiments, we use a encoder, 6.7 billion parameter language model pre-trained on code. The reason is it's generating SQL queries, so we want a model that's good at working with code. Yeah, so the first hypothesis in this case that we're looking at is context distillation can outperform directly learning with gradient descent. So we're going to see, can this process of distilling training examples actually outperform, just training on those training examples. And so the setup looks like this. We have a teacher model with a table schema and 4 in-context examples, and then a raw input question, and then a student with just the table schema. So it has to distill these 4 in-context examples. Yeah, and then for the gradient descent case, it's the same prompt as the student, except it's, instead of distilling the 4 context examples, we just do normal fine-tuning on the XY pairs. And what we see is that so the teacher has 27.7% accuracy on 4 training examples, 28.2 on 8 training examples. Before distillation, the student does really poorly. So these training examples actually were helping the teacher in the prompt. And then after distillation, if we distill these 4 or 8 examples, we actually outperform if we were to do gradient descent on these 4 or 8 examples. So, and we also see that, if we distill more examples, we learn even more. So this can actually be, at least on these small data sets of 4 or 8 examples that we tested here, a substitute for gradient descent. Yes, directly learning with gradient descent equals normal fine-tuning. So this is just like fine-tuning with Adam W on these training examples. I guess it's not, vanilla gradient descent, but yeah, what we meant by that is just normal fine-tuning. Yeah, so this is pretty interesting. Yeah, so we can actually outperform gradient descent. And then the next question is, can we learn from more training examples than actually fits in the context window? So you might say, like, why would you need to do context distillation if you can already just prompt the model and get something that's slightly better? There is a drop. There's always a little bit of a drop when you distill. It doesn't fully recover the teacher's performance. But it might be the case that you can't fit all the training examples in the teacher. And maybe if you distill more training examples than could fit in the teacher's prompt, then you might be able to significantly outperform the teacher with context distillation. So to test this, we have sort of the same setup where you have 4 in-context examples in the student schema. But we chose 4 databases which have really long database schema, and we can fit 4 training examples in the prompt, but not 8. So to distill all 8 examples, we distill multiple prompts which have different subsets of these 4 out of the 8 examples into the student, and we see that the student before distillation, which represents sort of the average teacher, we actually can, hold on. There's an error in the slide. So the student has 4 in-context examples as well as the teacher. So the student has the most examples you could fit. But if you distill 8 examples with multiple prompts, you can actually improve over the 4, is what this is showing. There's an error here in this slide. That's my bad. Yeah. So the takeaway here is that you can actually distill multiple prompts with different in-context examples, and you can outperform, what the teacher could have done with a single prompt. This is a sort of a advantage of context distillation, is you can actually outperform the teacher if you, distill multiple prompts with more training examples. Okay, so that's the learning from training examples part. The last part is learning from step-by-step reasoning. So we can use context distillation to learn from these reasoning processes in some sense. So our setup, we define an input distribution. So it's basically, we look at this addition task, and we consider all 1 to 8 digit addition questions. And we have an answer extractor that basically just pulls the final answer out of the teacher's scratchpad output for training the student. So the first hypothesis is, can we actually internalize the step-by-step reasoning processes? And so we do this by first giving the teacher a prompt that contains instructions to do a scratch pad, to use scratch pads. And the student is given a prompt with just instructions to directly answer the addition question. The teacher is this T5 small model that we fine-tuned on 500 scratchpad addition questions. So the T5 small model can't out of the box do addition. We have to fine-tune it to first give it this ability. But you can imagine larger language models could do this few shot. And we compared to 2 baselines. One is sort of this transfer learning baseline, where we fine tune on 500 scratchpad examples and then fine tune on the direct answer, to directly answer from those 500 examples. So this is testing whether these 500 examples, first learning scratchpad would help it, skip to being able to directly answer. And then there's also this multitask baseline of doing both tasks, essentially, direct answer and scratchpad. And we see that actually, if we do distill the chain of thought, the student after distillation, so this is the teacher's performance, 93%. Before distillation, the student has 0% accuracy. After distillation, the student actually outperforms the teacher by a little bit at 95%. And then these two baselines I described are quite a bit lower. So we actually are able to sort of effectively internalize the step-by-step reasoning in this addition setup. And then the final hypothesis in our paper takes this a step further. And basically, we want to see, can the reasoning abilities that we learn from the scratchpad distillation actually transfer to related reasoning tasks? So when we're doing the scratchpad distillation, we're sort of teaching the model like how to add numbers better, or helping it improve its reasoning abilities. So we want to see, does this general improvement in reasoning abilities actually transfer to other tasks that might not strictly be the task that we distilled. And so to test this, we took a larger teacher. So this is our 11 billion parameter T5 model that we fine-tuned on a mixture of our natural instructions data that we showed earlier, plus some addition questions, because there's not much reasoning data in the natural instructions data set. So it can't do addition out of the box if it's just fine-tuned on that. So we add our 500 addition problems to it. And now we have a sort of a language model that can take tasks instructions and complete any task you describe, but also do reasoning tasks. And then when we distill the student, in addition to just training it to maximize the likelihood of the teacher's answer, we also mix in a bunch of random natural instructions data so that it doesn't forget its ability to respond to other prompts. This sort of gets at the question from earlier about does it just learn the task being distilled, or can it also do other tasks? So if you mix in other data sort of in like a multitask sense, you can keep some of the prior abilities. And so once we do this, we see that the student, its ability to directly answer these 8-digit addition problems improves from 1% to 17%, while it remains, unchanged essentially in its performance on natural instructions V2. And then we also see that if you take like related reasoning problems that aren't strictly what we distilled, there is actually an improvement. So we have these kind of problems. We tested on a few, but like one example is, A has 7 turkeys, B has 2 turkeys. How many turkeys do they have altogether? Instead of, just add the numbers, you could rephrase it as different word problems, doing these sort of related addition tasks, but not exactly the same. And we see that, these related tasks performance also improves from 17% to 30% after we distill the addition. So there is actually some transfer of the reasoning abilities. If we distill the step-by-step reasoning, the knowledge distilled actually does sort of transfer to related tasks. At least this is some evidence to support that. So didn't finish too early. That's my full presentation, and happy to take questions.
Okay, so while we wait for more audience questions.
Sounds good.
A general question I have is like, when shouldn't you use context distillation?
So I would say, part of it will be, I think, an empirical. So in a lot of the things we tested, there's not really good methods for learning from natural language explanations, for example. I think context distillation might be one of the few candidates there. For learning from step-by-step reasoning, I guess you could fine-tune it somehow. So maybe it's just an empirical question there. For learning from concrete examples, I would say there is sort of a clear trade-off. So if you say have a very large data set, I'm pretty sure that just normal fine tuning will be context distillation. But if you have like a smallish or medium-sized data set, there's might be an advantage to context distillation. So there's sort of this trade-off of how much data, and it also might depend on the task. So this task that we looked at was this semantic parsing task, where there sort of is a lot of like compositional reasoning that's happening with respect to the in-context examples. Like if you have a in-context example that has this, how old is peak? And it says, select name with age, then maybe if you asked the question where was peak born, it could, use some of the knowledge from the actual example, like this part, where name equals peak, might actually be useful for answering, related questions. So in some tasks, what I'm trying to get at is in some tasks, using the knowledge in the in-context examples might be more useful than others. So I think it really just depends on the task and like how much data you have, things like this.
Got it.
The size of the student matter.
Yeah, I have another question, which is, does the size of the student model matter for in-context distillation results?
Yeah. So if we go back, a big part of this is that the student, this is how this differs from normal distillation, is that the student and the teacher in this case have the same parameters. So the student should be the same size as the teacher, at least in our framework. Now, the teacher needs to be a certain size for it to be able to do in-context learning. So that's why we were using like the largest model we could, which is this 11 billion parameter model for most of our experiments. We took the largest model we could. And this is because you need a certain size model for it to be able to do in-context learning. Yeah. And so this result of context distillation, we do generally expect that it should work better with larger models. So we tried it on 11 billion parameter models, but if you go even larger, this stuff should work even better. Yeah, is our hypothesis. We can't test it though, because we didn't have enough compute. Are there any interdependencies between how much effort it takes to forget something by recursive overriding to remember several different tasks when we add tasks?
This one is kind of
Task sizes, specificity, learning overload. How much effort it takes? I'm not sure I fully understand the question. So I guess I can, or do you have?
I think it's something like related to, I guess, like the effect of the tasks, right? So they're asking if there's some kind of interdependency between, for example, the teacher and student size and the task specificity and learning load.
Yeah. So what I will say is like, what we found is like, there is this, so when you do the recursive distillation, you're training the student to, respond to a simpler prompt than what the teacher originally took. And so there's some risk that the student will catastrophically forget how to respond to different prompts. We find that at least with the large models that we are fine-tuning, this isn't too big of an issue. So after even multiple rounds of this recursive distillation, it still remembers how to respond to these prompts. Now, if you did more steps, maybe it would forget. And maybe this is specific to the tasks we considered. Yeah, but we found it not to be a huge issue. One way to get around this could be like we did in the last experiment, to just mix in general, in-context learning data to help it retain to force it to retain some of its abilities. But yeah, that's sort of what we found, is that we didn't study this trade-off too extensively, but we found that it doesn't catastrophically forget immediately, at least.
Okay, let's see if we don't get another question in 1 minute. I think we can end here.
All right, sounds good.
How did you come up with the idea?
I mean, a lot of it was actually just this like inspiration that we talked about at the beginning. Just like, how do humans do it? Just thinking like, okay, there is sort of this strange thing where like these models, like they have to use these like long reasoning chains, etc. If we actually want the models to solve more complicated tasks, this might be a bottleneck, especially considering limited context length. And so we were like, okay, how do humans do this? Can we come up with some analogy? That was sort of the starting point for this research. Yeah.
Got it. Cool. Okay, we have our final question. So, sorry, maybe I could be wrong, but is the main benefit from context distillation to reduce prompt length?
I think fundamentally that's the reason. So reduce prompt length, reduce the need for the reasoning chain. You're using less inference compute. This is all part of the benefits to this. But you could imagine like if you repeatedly apply context distillation, you're sort of doing some analogy to what I described at the beginning, which is you're distilling this knowledge with practice deeply into the model's parameters. And if you do this on simple tasks, you might be able to build up the skills to do more complicated tasks. Now, we don't have too many experiments to validate this more complicated version, but this is sort of the vision, at least. Our last experiment sort of hints at this, which is that if you distill like this step-by-step reasoning ability into the model, it actually transfers to other related tasks. So there's like actually some skill transfer. But yes, fundamentally the thing is you're saving context when you do this.
Okay, and I think that's a wrap. Thank you very much for the talk, Charlie.
Yeah, thank you for having me.